let's start with just redefining a polynomial. So remember, a polynomial is a function made up of coefficients. What's a coefficient?
Yeah, we don't got this paper.
Wait. So a function has coefficients. A polynomial is a function with coefficients and positive whole exponents. So remember, that means no variables in the denominator and no roots. Okay. So we will deal with one variable polynomials in this. So we're just going to deal with like all x's or all y's in the polynomials that we do. So standard form of a polynomial is written from the greatest degree exponent to the least. So you always start with the highest degree exponent in the front, and then you go down until you get down to basically your constant, just your number. So for example, if we have x squared minus 3x to the fourth plus 7x minus 10 plus 5x to the third, what is the first term going to be in standard form?
Negative 3x4.
Yeah, because x to the fourth is our largest exponent. That's going to go first. You keep the sign with the coefficient. So negative 3, x to the fourth. And then we're just going to go down order of exponent degrees. So plus 5x to the third plus x squared plus 7x. Did we do this? Well, it just comes back because we really have to pay attention to it, like now. So we need it in standard form because the leading term tells us the degree of the polynomial. R first is y equals a number. Okay? This is technically an exponent with a degree of 0 because x to the 0 power, anything to the 0 power is what?
0.
1. 1. Anything to the 0 power is 1, so we don't need to say 2 times x to the 0 because that's 2 times 1, which is just 2. Okay, so we call this a constant function. And what it looks like is just a horizontal line. Okay? So then moving up to our next degree would be x to the first, y equals x, right? There's technically an exponent of 1 on that x. Because what's there if we don't write an exponent? Yeah, so this is the first degree. And we call this a linear. Because linears have x to the first power, like 3x plus 2.
Wait, why is there a 1 on the x but not a 1 on the 2?
There is a 1 on the 2. We just don't write it. There is. Anytime there's not a written exponent, it's implied that it's 1. Okay? Y equals x squared. Now we can see the degrees. This is to the degree of 2. How do we name this function? Anything squared is a, quadratic. Quadratic. And its shape is a parabola. Y equals x cubed. To the third degree, we call this a cubic function. And what it looks like is kind of like an S.
Why is
like on its side. Quadratic.
Why is it called quadratic? It's 2.
That's a great question. I need to look that up.
It should be a 2.
Yeah,
That's actually
it is such a great question.
I was scared to say it because someone was just going to call me stupid.
Well, I'm glad you said it because everyone was thinking it. Okay, this is to the fourth power. We call this a quartic. And it looks like a kind of like a W. So like this. Quartic. And the last one we'll talk about, we won't, see this a ton, but to the 5 is the 5th degree. We call this a quintic. And this one looks like a cubic, but it has an extra little turn, so it's like something like that. okay? Describes where a graph is headed. Graph is headed in both directions. So to the left and to the right. We will use the arrows on the end of our function to help us determine end behavior if we have arrows. Okay, to write end behavior to the right, we say as, x approaches infinity. That means to the right, right? Because this direction to the right is headed to positive infinity. So end behavior to the right, we always say this, as x approaches infinity. End behavior to the left, we'll say as x approaches negative infinity, because negative infinity is to the left on our x-axis. The end behavior will be where the arrows of the function are headed. So then we're looking at the right arrow and the left arrow in order to talk about end behavior. Okay, so look at each arrow. When we have a graph, it's pretty easy to do end behavior. So like if you have a graph, that's great, but you won't always. So for this first graph, we're going to start to the right as x approaches infinity, and you have to write the whole thing for the end behavior. To the right, where is y headed? Positive infinity. And then to the left, as x approaches negative infinity, we'll look at our left arrow. Where is y approaching? Negative infinity. Let's do the middle one. So to the right, as x approaches infinity, we're going to look at the right arrow. Where is y headed? Okay, negative infinity. So you say y approaches negative infinity. And then to the left, as x approaches negative infinity, y is approaching what? Also negative infinity. Okay, oops, not 8, infinity. Okay, now that's great if we have a graph. We can look at the arrows and determine end behavior, but we can also determine end behavior by looking at the leading term of the polynomial when it's in standard form. So if you get into standard form, the leading term, the first term in that polynomial will tell you the end behavior, okay? So if you don't have a graph, you can still figure it out if you just have the equation. Okay, if you have an even exponent and a positive coefficient, so something like this, y equals, let's just do a quadratic. Y equals x squared. Do you see how the exponent is even and the coefficient is positive? It's a positive 1. Think about this graph, right? If it's a quadratic with a positive in front, it looks like this, right? It's concave up. This is true for any even exponent. So if it's to the 4th, to the 6th, to the 8th, with a positive coefficient, both sides will always face up, okay? So the end behavior will always be to the right as x approaches infinity, y is going to be approaching infinity. So both sides are going to go up. And as x approaches negative infinity, y approaches infinity. So you can think of the shape of just a regular parabola with a positive coefficient. This will apply to any even exponent. What if we have an even exponent with a negative coefficient, like negative x squared? What happens to my parabola? It flips. Okay? This is true for any positive or negative coefficient with an even exponent. So you have negative x to the 4th, negative x to the 6th. It will flip the function upside down, and the end behavior becomes negative infinity in both directions. Okay, those arrows point down. For an odd exponent, think of just like a linear function. Okay, that's technically an odd exponent of 1. And it has a positive coefficient because it's just a positive 1 in front. Think of it like a linear function. Left to right, if it's a positive slope, it is going to rise. Okay, always. And that's true of any odd exponent. So to the third, to the fifth, with a positive coefficient, it will rise from left to right. In between the end behavior, you might have different curves based on how high the exponent is, but the end behavior will always be the same if it has an odd exponent and a positive coefficient. So to the right, as x approaches infinity, y also approaches infinity. So we're looking at this right arrow. And so then to the left, as x approaches negative infinity, y also approaches negative infinity. So looking at this right arrow, or sorry, to the left arrow, it is going down. If you have, let's just do this, y equals negative x. If you have a negative coefficient and an odd exponent, so think of a linear with a negative slope, from left to right, it will fall. And this is true of any odd exponent. So first, third, fifth. What changes is what's happening in between the arrows, but the arrows will always be the same, the end behavior. So this is going to be to the right as x approaches infinity. Y is going to negative infinity now. And to the left, as x approaches negative infinity, y is going to positive infinity. So the leading term tells us a lot. The degree of the polynomial, so we look at the biggest exponent, right, that first term in standard form, also tells us the number of possible real zeros the graph will have. So the degree, if the degree is 3, this could have up to 3 zeros. And remember, a 0 is where it crosses the x-axis. So you could have up to 3 zeros in a cubic. X to the 6, how many zeros could you have? Up to 6. You don't always have 6, but you could have up to 6. You'll never have more. Up to 6, up to 3. So the degree tells how many possible places it's going to cross that x-axis. So we can start from our function and talk about the end behavior. Or we can look at the graph. If you look at the graph, you should be able to tell me about the leading term. So is it negative? Is it positive? Is the degree even or odd? By looking at the graph. We have this graph where both arrows are going in the same direction. What does that tell us about the degree of the polynomial? If they go in the same direction, is it even or odd? But you're right, it is negative. It is even because they're both going the same.
Even and negative.
Even, and because they're facing down, we know that the coefficient is negative. Okay? For the second one, look at your end behavior. They are going in opposite directions, meaning, is this even or odd? Odd.
It's odd.
Okay, and it is rising from left to right, meaning it is positive. Right? So it's going rising from left to right. So it is a positive coefficient.
This next one's even positive.
The next one's, yes, going to be even because they go in the same direction. So we know that the exponent would be 2, 4, 6, 8, etc. And they are both going in a positive direction. So we know that the coefficient was positive. Knowing all this, I expect you to be able to give me a decent graph using the end behavior and using what you know, what you can find from this function. So to sketch a graph, here's our steps. Number 1, determine the end behavior. So we are going to look at the, leading term, even, odd, positive, negative, and find the y-intercept. Then we can make a function table, because I'm making you do this because I feel like this is something we're weak on, that we don't remember that we can graph any function by choosing an x value and getting a y value out so that we can do ordered pairs. So I want to just practice this because I feel like sometimes you get stuck and you don't know how to graph stuff. This is how you can always graph if you don't have a calculator. Step 1, let's look at this function. What is the leading term? Always check that it's in standard form. Sometimes it's not. This is in standard form. So what kind of leading term do we have? Odd or even? Odd. Positive or negative? Positive. Meaning my end behavior is going to look like this. Right? It's going to, left side's going down, right side's going up. How do I find the y-intercept of this function? The y-intercept occurs when x equals 0. So what we do is we plug in a 0 for every x, and that'll tell us our y-intercept. What 0 plugging in does is it makes every other term 0. So 0 plus 0 minus 0 plus 1 is what? 1. So my y-intercept is 1 here. So I can plot that little point. And then I'm going to plot at least 3 other points. And the way that I can do this is by using a function table. So if you don't know how to graph and you don't know where to plot points, you can always make a function table and figure out x's and y's. In a function table, you choose the x. So I'm going to do like -1, 1, 2. I'm not going to do 0 because we already know the intercept. Okay? This will give us 3 other points that we can plot. So if we plug in -1 to our function, go back to the original, and we're going to plug in a -1 for x, and then just do the math. So -1 to the third plus 2 times -1 squared minus -1 plus 1. And this is where, like, if you had a 4-function calculator, you could have it help you with this arithmetic. Okay, -1 to the third is still -1. When you do this, be super careful. Order of operations, you must do this first. What is -1 squared? +1. And then +1 times 2 is 2. Do not do 2 times -1 and square it. You'll get the wrong answer. Then we have minus a -1, which turns into +1, plus, and then our +1 at the end. If we do all of this, 1 plus 1 plus 1 is 3. So we have a point. This is an ordered pair. -1, 3. So I know I have a point right here.
And you can do on the other side.
So then, yeah, so well, no, because it's not a parabola, it's cubic, right? If it was a parabola, you're right, we could mirror it, but it's not. So we have to figure out, we have to do the math, which is like a bummer, but like it's also math class, so we will do math sometimes. All right, let's plug in 1. 1 cubed plus 2 times 1 squared minus 1 plus 1. 1 cubed is 1. Do this first. 1 squared is 1 times 2 plus 2 minus 1 plus 1. So what do we get? 3 again. So let's plot that. It does mirror, but that is just lucky. It's not always going to mirror. So let's do 2 because it's going to show us where our function's heading. If we plug in 2, we get 2 to the third, yep, which is 8. So 2 to the third plus 2 times 2 squared minus 2 plus 1. So 2 cubed is 8. So 2 squared is 4 times 2 is 8 minus 2 plus 1. So 16 minus 2 is 14 plus 1 is 15. So this point, look, is going to be way up here. 215. So it's going to be like way up off of the thing. Now, our end behavior is how we're going to finish this function. Remember, on the left, it is going down. So this is going to look like this. Our end behavior is going down. To the right, our end behavior is going up. So we'll connect these and then continue our arrow going to a positive direction. X to the fourth. Let's start by identifying our end behavior. So this is standard form. It will be even with a positive coefficient. So what are my ends going to look like? Up, up, right? So on either side, our arrows will be like this, okay? Then let's identify our y-intercept, which occurs when x equals 0. So we plug in a 0 for every x. I'm trying to cover the x's. 0, 0. So these all become zeros. Where's our y-intercept? -6. Yes. Pretty much. The only time you can't is like sometimes they'll give you it in factored form. And then you have to plug in, 0 plus 2. So not always, but if it's in standard form, yeah, it gets rid of all of your terms. Okay, so y-intercept at -6. Let's graph that. So that's down here. We can graph our y-intercept. Now we need to find a couple other points that we can plug in and determine some other exact points that we can graph. How we do that without a calculator or a graph given is we choose values to plug in for x. Yep. I'm going to do the same ones. I like to kind of see on either side. The problem is when you have like higher order degrees, they get really big really fast and we can't really graph them on a 10 by 10. Yes. Okay. -1 to the 4th power will be +1. So -1 4 times.
So -1 for the first one.
So then, yeah, so this is minus a -1.
But then it's minus.
So then it'll be plus. Order of operations. +1. So then 2 times +1 minus 2. -4 minus 6. Yikes.
Why is it -6?
Because that's part of our first problem.
Oh, yeah. -12.
Okay, so 2 minus 2. -10. -1, -10. This is an ordered pair. We can put this on our graph. -1, -10. That's way down here.
What?
Right? -1, -10. Because this was -10. Yeah.
-12.
1 plus 1 is 2. Minus 2 is 0. -4 minus 6 is -10. Okay, so if we plug in +1, do all the math, we get another ordered pair. 1, -4. Oops, I'm going to do that in blue. 1, -4. Okay, from here, yes. This graph, let's put in our end behavior. Okay, we know that it's even positive. Both arrows are going up. So from our last one, this is going up and this is going up. And then this has to somehow, oops, not like that. It's going to curve through both. That is like the ugliest graph ever, but it gives you some kind of an idea of what it's doing. What I am looking for is that you have these points and that you have this end behavior. The thing that you can't do is connect them with a line. They have to have the curve.